Hello and welcome. In this lesson, we'll go over the process of graphing a rational function of the form f of x equals quadratic over quadratic. Step 1. Factor the denominator. This will help us find the zeros of the denominator, thus the domain of the function. The domain is any real number x such that x is different than the zeros of the denominator, or as we call them, the restrictions. Another thing we'll be able to get from the zeros of the denominator is the vertical asymptote. The vertical asymptote are equations of the form x equals the zeros of the denominator or the restrictions. Next, we would have to find the horizontal asymptotes. Horizontal asymptotes will also help us determine the range of the function, which will be y any real number such that y is different than the horizontal asymptote. Next, we find the intercepts. The x-intercepts are found by making y equal to 0, and the y-intercepts are found by evaluating the function at x equals 0. Then we determine the end behaviors. There are two types of end behaviors that we need to look into. The end behaviors that will help us find what the values of y become as x approaches infinity, and what the values of y become as x approaches negative infinity. Another end behavior that is worth discussing is what happens to the values of y as x approaches the vertical asymptote from either the right or the left-hand side of it. And then lastly, you put everything together to draw the graph, all your findings. So let's take a look at our example. Kx equals x squared plus 1 over x squared minus 1. I will factor the denominator, which in this case is x plus 1, x minus 1, difference of squares. And this will help me determine the restrictions. So we'll say x plus 1 is different than 0. And x minus 1 has to be different than 0. So x is different than negative 1 and different than positive 1. So the domain of the function would be any real number x such that x different than plus or minus 1. And since we're here, let's state the asymptotes, which will be at x equals positive 1 and negative 1. Next, we determine the horizontal asymptote. For the horizontal asymptote, if you remember from the previous lessons, we said that we check with the highest degree term of the function. The highest degree term in this function will be degree 2. And then we compare the leading coefficients, or the coefficients of the highest degree term function in this function. And this one would be coefficient of 1, x squared in the denominator coefficient of 1, which tells us that the horizontal asymptote will be y equals 1 over 1, or simply y equals 1. And since we're here, let's take the range. And the range is any real number y such that y is different than the horizontal asymptote, which is at 1. Next, we'll look into the x and the y intercept. For x-intercepts, we make y equal to 0, which means that 0 equals x squared plus 1 over x squared minus 1. We can solve this simple rational equation by cross multiplication, or we can also solve the equation by making the numerator 0, because basically a division will be equal to 0 if the numerator is 0. So that tells us that we are looking for x squared plus 1 being 0, which means that x squared has to be negative 1 and x is plus or minus negative 1. Plus minus negative 1 is a non-real number, it's an imaginary number. Therefore, we're going to say that there are no x-intercept on the real Cartesian plane. To determine the y-intercept, we are setting x equal to 0. And remember that we've explained that before. For the y-intercept, we're going to have the ratio of the constant terms. But if we don't want to remember too many things, then here we go. We're going to write y equals 0 squared plus 1 over 0 squared minus 1. And that will give 1 over negative 1. So the y-intercept would be at negative 1. So these are our findings so far. We have found the asymptotes, both horizontal and vertical. And we've also found the intercepts, both x and y intercepts. And there is no x-intercept, but there is a y-intercept at negative 1. So since we're here, we are going to put everything on the graph. So I will draw the the vertical asymptotes at 1 and negative 1. So here is the vertical asymptote x equals negative 1. And here is the vertical asymptote x equals positive 1. And the horizontal asymptote, which is at y equals 1. I would label the asymptotes by the respective equations, and I will draw arrows at both ends of each. So this is the horizontal asymptote, y equals 1. And here we go, a vertical asymptote of negative 1 and vertical asymptote at x equals 1. There are no x-intercepts, but there is a y-intercept at y equals negative 1. So far, this is what we want to know. There is a practical way and a more analytical way of drawing the graph of a function. I'm going to go over the practical way first. And I'm going to write down here. So the practical way. Our method. All right, so this is how we can draw or figure out what the behavior of the graph will be. Remember that graphs of rational functions are curves that follow their asymptotes, which means that we need to focus on all the sections that have been formed by the asymptotes. So we have these two vertical asymptotes and this horizontal asymptote, and they have created the following sections on the Cartesian plane. And for each part of the domain, remember that the domain is cut off by the vertical asymptotes. For each part of the domain, we'll see the graph appearing. For example, from 1 to infinity, the graph will appear either on this section or on this section, because the graph has to follow the asymptotes. So this is why we refer to points that cut off the domain in order to determine where the graph will be. So we take a number to the right of 1. So for x bigger than 1, we pick a value, for example, x equals 2. So evaluate the function at 2, and we'll say that k of 2 equals 2 squared plus 1 over 2 squared minus 1, which makes it 5 over 3. That tells us that the function at x equals 2 will have a value of 5 over 3, which is going to be 1 and 2/3. So 1 and 2/3 will be somewhere here. The fact that the point or the graph will have a point here tells us that the graph must be located in this section that is formed by this vertical asymptote and the horizontal asymptote. So I can draw the graph here with confidence. Okay, let me try one more time. Again, remember that this is a sketch. It's not a precise graph, because in calculus you learn how to draw them with a little bit more precision. And then we check and see what happens in the domain between x equals negative 1 and positive 1. So for this, what you want to do is pick any number in between negative 1 and 1 and see where the y values are located. Now, since we're looking into this domain, so into these x values, then the graph must appear either in this section or this section on the Cartesian plane that is defined by the asymptotes. Now, since we already have a point and it's located in this section of the graph, it's a y-intercept, then we are going to say that the graph must be over here. And then we're going to say that for the function to follow the asymptotes, remember we do not have any x-intercepts, it means that the graph is going this way around. So we're going to draw the graph. Because we don't have any asymptotes, that means that the graph is not going to continue this way. It cannot continue this way because it can, if we draw the curve in this direction, then the curve will have to intercept the x-axis, which means x-intercepts, and it will have to intersect the horizontal asymptote. So for the last section of the domain, which is x values less than -1, we're going to pick a value of x, which is at -2. So I'm going to jot a few notes in here for this section that we just finished. So from -1 to 1, we use the existing point, which is the y-intercept. And we draw the graph so that it follows the asymptotes. Now for x values less than -1, we choose x equals -2 to evaluate the function. So we'll have -2 squared plus 1 over -2 squared minus 1, which will give 4 plus 1, 5 over 4 minus 1, 3. So that means that we're going to have a point somewhere in here, which means that the graph, which has to appear either in this or this section, will be in the section above the horizontal asymptote, and this will be the shape of the graph. As you can see here, there is symmetry to this function, and this can be proven actually by finding k of -x. So k of -x would be equal to -x squared plus 1 over -x squared minus 1, which is x squared plus 1 over x squared minus 1, which tells us that k of -x is exactly the same as k of x. So this function will also have even symmetry. And very often we can use even symmetry to draw the graphs faster, because when we know that the function is evenly symmetrical, then we can draw half of the graph and then figure out the rest of the graph based on its symmetry. About the end behaviors, then, we are going to say that as x approaches infinity, the values of y will approach 1 from above. The reason why is because we see that as x approaches infinity, the values of y will stay above 1, above the horizontal asymptote, which is 1 plus. As x approaches negative infinity, the values of y will approach, let's take a look, x approaching negative infinity, the values of y will stay above 1, so 1 plus. Then we can check and see what happens at each side of the asymptote as x approaches the value of 1 from the right-hand side. Here is x equals 1. Here is the right-hand side of the vertical asymptote. And as you can see that the graph is going up, which means that the y values will approach infinity. When x approaches the vertical asymptote at 1 from the left-hand side, you see that the graph continues down, right? So it's heading down. So we'll say that x approaching 1 minus, y is approaching negative infinity. Next, x approaches negative 1 from the right-hand side. So here is x equals negative 1. from the right hand side, -1 plus. The y values are approaching -infinity. And as x is approaching -1 from the left-hand side, so here again is -1, here is the left-hand side, the y values are going up. So they're going towards infinity. So this is a practical method of graphing a rational function, the method that we use most of the time. And in the next example, I will show you the more sophisticated analytical method of drawing the graph of a rational function. So I hope this lesson made sense. Let me know in the comments if there is anything else that you would like me to explain or talk about, or even if you have any questions. Thank you for listening, and thank you for choosing to learn from me. Bye for now.